My name is Greg Nilgis, and today's video will be in support of Sonoran Desert Institute's FTH 202 Revolvers Module 3 assignment. Today's date is 11 May 2024, and there is no live ammunition within this workspace, nor there will be throughout the video, and I will show a safe and clear firearm, no ammunition visible or physically present. And we'll try to do that as needed throughout the video for each segment. The references I'm using for this particular module assignment is the lecture, Module 3 lecture, as well as this very good book from Patrick Sweeney, 3rd edition of Gunsmithing Pistols and Revolvers. Gleaned some information out of that, but most of the information will come from the lecture and the material presented there within. Okay, this is part one of the video, and first and foremost, we're going to say that because it is true that there's no live ammunition in the workspace, and we're going to visually and physically inspect the cylinder. There's no ammunition in the firearm. We have a safe firearm, a safe work area, and this part one video is going to talk about failures of specific components within the Taurus 8.56 and similar designed double action revolvers, single action, double action, I should say. And I'll define a failure as any part that doesn't function as it's intended. It could be a part that breaks in use or abuse, or it could be a part, in my opinion, that is manufactured poorly or incorrectly. First, we're going to talk about the hammer strut. Of course, the hammer strut gives the mainspring a place to live and a method for the mainspring to act on the hammer. If the hammer strut is damaged, say the tip of it's worn down, or the hammer strut itself is broken, the spring will have no method to act upon the hammer, so you would have an inability to cock, failure to cock, as it were, and obviously you wouldn't be able to fire. Would it be a failure to fire? I'm not going to say it is, because you can't even cock the firearm, so if you can't cock it, you can't fire it. So that kind of, you could almost say it's you couldn't chamber it either, but in addition to a breakage or something like that, if the hammer strut was bent, it would cause binding, or it could cause binding within the hammer spring, and that would also cause cocking issue, failure to cock, and subsequent failure to fire. And additionally, if it's manufactured such, you can't see it here with the spring, but there are flat surfaces on the hammer strut itself, and if they had any burrs on them, the hammer could catch on them in the compression stroke, and that would basically, although you'd probably be able to cock it, it would definitely increase your felt force, or muscle force required. So on to the next part, we'll talk about the hand. The hand is directly involved in chambering, and I say indirectly in locking because the locking is done. We'll talk about that in a minute. So we got the hand here. The locking is done by the hammer, or the cylinder stop. Locking's function, based on acting by the trigger raising it, is to rotate the cylinder, and it rotates it such that it becomes the topmost cylinder will be obviously in line with the bore, and the cylinder stop will lock it in. So if the hammer, or the hand rather, was damaged, the tip of it were damaged or whatnot, it would be obviously a little shorter than it should be. So the cylinder would likely not rotate far enough to chamber and or align the top bore with the top most chamber with the bore, and so you'd have a failure to chamber there. If it was completely broken, you wouldn't even be able to rotate at all, so you'd have subsequent failures with that. On to the cylinder stop we just talked about. Cylinder stop is directly involved in locking and indirectly in chambering, just because it locks in when the chamber's at the top. So if the cylinder stop was malfunctioning, due to wear and tear or whatever the case may be, it wouldn't be able to lock in the subsequent recess in the cylinder, and you would have a failure to lock. I would also say that if there was debris or something jamming it up, or if there were burrs preventing it, or some kind of breakage internal, you may even have a failure to unlock when the trigger acts on it right here in this area. If something was preventing that from happening by the failure of the cylinder stop, then you wouldn't even be able to unlock the cylinder. And last but not least, we'll talk about the sear surfaces on the trigger. I say there's two of them. This one right here, I call a single action sear. And when you pull the trigger back or the hammer back manually, this topmost sear surface will engage the hammer hook or the notch in the hammer, and it will keep it in the cocked position. If that sear surface on that trigger is broken or damaged, you may very well not be able to cock the hammer, or it wouldn't hold the hammer in position. So in the single action mode, you wouldn't be able to cock it. So you'd have a failure to cock. If you can't cock it, then you can't fire it in the single action mode. So you'd also have a failure to fire. And second to that, you can't see it. This second right down here is what I call a double action sear. In the double action mode, it as you pull the trigger back, it catches or rides on the hammer, the lower part of the hammer, and once it reaches full cock position and everything is locked up, the hammer will fall off of that surface. And if that surface on the trigger is damaged sufficiently, the hammer will prematurely fall off. So even though you may be able to partially cock it, and it may even look like it's all the way cocked, you won't get full cocked, so you will have some degree of a failure to cock. And depending on how far that is, how soon it falls off, if it falls off too soon, you won't have enough inertia working on the hammer through the mainspring to impact the firing pin sufficiently to perhaps ignite the primer, and you would have a failure to fire. So again, failure to cock may or may not be a problem. You may get it fully cocked, you may not, but regardless, you're going to have some impact to the cocking cycle of operation, and subsequently you may very well have failure to fire following that up. All right, for part two of this video, we're going to demonstrate the process to measure the twist rate in the barrel. First of all, there's no ammunition in the workspace. We have a non-functional firearm because the cylinder is locked open, so we don't have to worry about that. The reference for this, where I got the reference for the twist rate for the barrel, is Taurus USA's website under the tech specs for the model 856 revolver. So first we've got a cleaning rod in here. We've got a flag at the 12 o'clock position, a mark at the 12 o'clock position on here, one about the 1/8 of a rotation of the barrel, and one as the patch enters the bore. So we're going to push this through until we reach about 1/8 rotation on this flag, and then we're going to make another mark so we can measure the barrel or twist rate. There we go, right about there. All right, I'll pause this video and we'll come back and measure that and do the math. Okay, for this segment, no live ammunition and no firearms, so we have a safe work area. The reason we're doing this measurement is because certain twist rates prefer certain heavier or lighter weights of bullets for better accuracy, and this is not just a revolver or a handgun thing, it goes for all firearms. Very, very specific, particularly for rifles, in my opinion. So what we did was we made a mark on our clean rod where with the top dead center where it entered the bore and where it reached 1/8 rotation as we pushed through. So I estimate this distance to be 2 1/16, and 2 1/16 inches is, I think, 2.06 something. Let's call it 2.06 for ease. And if we now since we rotate it 1/8, we're going to measure this distance by 8, and that'll give us our twist rate. So 2.06 times 8, if I'm not mistaken, is 16.48, and Taurus website says the twist rate for this 856 is 16.5. So I believe that's good. I will say this in closing, with very few seconds remaining, that this is much easier done on a longer barrel. A shorter barrel, it's hard to get an accurate reading because you just don't have much room to work in the barrel before you push it out the other end.